You know, concrete, it's literally the foundation of our world. It's in our skyscrapers, our bridges, the sidewalks we walk on every single day. But what if I told you that inside this boring gray material, there's a hidden universe of incredible chemistry and microscopic structures? Well, today, we're going to go deep inside to uncover the secret life of concrete. We all see the final product, right? This solid, super strong material. But the real magic, the secret to its unbelievable strength, happens at a scale you just can't see. We're about to go on a journey deep inside one of the most common materials on Earth to figure out how a simple powder and some water can come together to hold up a massive skyscraper. So, to really understand concrete, we need to zoom in. I mean, way in. We've got to go past the big rocks and the sand and get right down to the paste that's holding everything together. And then we need to go even further, to the individual grains of cement, because that's where all the action really begins. Now listen, this is not just about stuff getting wet. Hydration is a complete and total chemical transformation. The very second that water touches a grain of cement, it kicks off this amazing chain reaction, building a brand new microscopic structure from the ground up that gives concrete all of its strength and durability. As a cement grain hydrates, it doesn't just form one single uniform thing. Instead, it creates two very different but equally critical structures. And these two have to work together to make the strong, durable material we know and rely on. All right, the undisputed hero of our story is this gel-like stuff called calcium silicate hydrate, or just CSH for short. Seriously, think of it as the super glue of concrete. It's the main thing that's formed during hydration, and it's responsible for basically everything, both the strength that holds up buildings and the durability that lets them last for centuries. Now, what's fascinating is that CSH kind of has two different personalities. First, you get what's called outer CSH. It forms really fast on the outside of the cement grain. It's more porous, almost like a temporary scaffold. Then, much more slowly, you get inner CSH, which forms right inside the original grain. This stuff is dense, it's super strong, and it provides the core strength that makes concrete so incredibly tough. Okay, but wait. This whole process, this construction of inner and outer CSH, it's completely invisible, right? It's happening on the micron scale. So how in the world do scientists actually peek inside and watch this hidden world come to life? Well, the tool for the job is a scanning electron microscope, or SEM. They use a specific technique that's kind of like giving an ultrasound to a tiny, polished slice of concrete. It's pretty amazing. The principle behind it is actually really simple. You fire a beam of electrons at your sample. Now, when those electrons hit a really dense spot, more of them bounce back or backscatter to the detector. So the rule is easy. The denser the material, the brighter it shows up in the picture. And this gives us this awesome visual decoder ring for reading these images. The densest stuff, the leftover unhydrated cement, shows up as bright white. That strong, dense inner CSH, that's light gray. The more porous outer CSH is dark gray. And finally, any empty space, the pores, just shows up as black. With this, we can literally map out this entire microscopic city and see exactly how it was built. This quote points to something called the wall effect. Now, in concrete, the walls are the surfaces of the sand and gravel, and the cement paste just can't pack as neatly right up against these surfaces, which leaves more space. This is exactly why you often see more pores and bigger crystals right at this boundary, which you can imagine can become a weak spot, a place where cracks and other problems can start. So, if we can see the structure being built, the next logical question has to be, can we control how it forms? And the answer is a huge, resounding yes. It all comes down to the recipe and the conditions you give the concrete while it's mixing and curing. The whole hydration process really boils down to three main stages. First, the surface of the cement grains dissolves into the water. Second, new crystals, like our friend CSH, start to grow out of that solution. And third, for the reaction to keep going, water has to find its way. It has to diffuse through these new layers to get to the unreacted cement core inside. And there are a ton of factors that can act like an accelerator or a brake pedal on these stages. For instance, the chemistry of the cement itself matters a lot. More of a compound called C3S is like a turbocharger for early strength. The fineness of the powder, the temperature, how much water you use, even tiny chemical additives, they all have a massive impact on how fast concrete gets strong. It's really part science, part art. But among all those factors, Two of them are like massive levers you can pull. If you grind the cement into finer particles, you create way more surface area for the water to attack, which speeds everything up. And just like in your high school chemistry class, if you increase the temperature, you accelerate all the chemical reactions. If you can master these two, you can really control how your concrete performs. Okay, so finally, there is one last absolutely critical thing to understand. This entire complex reaction. It's not happening in pure, clean water. The moment water and cement get mixed, that water transforms into this complex, ever-changing chemical soup. This special water is called the pore solution. I mean, within minutes, it gets completely saturated with ions that dissolve right off the cement grains. We're talking sodium, potassium, sulfates, you name it. This ionic cocktail is the true environment where hydration happens, and its exact makeup is super important. And the chemistry of this solution changes dramatically over time. In the first few hours, things like sulfate and calcium ions hit their peak, but then they get used up to build the solid structure. After a few weeks, all that's really left in high concentrations are alkali and hydroxide ions. This creates a very alkaline environment, which is actually a really good thing because it helps protect steel rebar from rusting, which keeps our reinforced concrete structures standing for a long, long time. See, understanding this microscopic world isn't just some academic thing. It is the key to making better, stronger concrete. It explains why water quality on a construction site is so critical, and it shows how just tiny amounts of chemical additives can completely change how concrete behaves, making it exactly what we need for the challenges of the modern world. From a single tiny grain of cement all the way up to a massive skyscraper, it's all built on this hidden and kind of beautiful chemistry. So the next time you walk on a concrete sidewalk, I hope you see more than just a slab of gray. I hope you'll imagine that dense, microscopic city built within. Thanks for joining this deep dive with The Explainer.